In this video, we're going to talk about discrete random variables. So the definition of a random variable is it's a function, we often call it x, which maps points in a sample space to real numbers. Kind of similar to a probability, although it doesn't have to obey any axioms. And many different random variables could be defined on the same sample space. Here's some examples. Let's say we had the one from last time, we're rolling a fair six-sided die. We could let x equal the number on the die, and then the range, the values that the variable could take on, would be 1 through 6. But we could also define y on the same sample space to be the distance from 3, and then y would be 0 through 3 only. Another example, let's say we roll 2 fair six-sided dice, then our sample space would have 36 points. We could let x equal the sum on the 2 dice, fairly logical, and then the range of that random variable would be 2 through 12. They wouldn't all be equally likely, but it could be any of those values. We could also let y be the maximum of the 2 dice, and then the range would be 1 through 6, or z be the difference between the 2 dice, and then the possible values would include 0 through 5, actually. So whatever the random variable is, its range, the values that the random variable maps to, also known as the support of the variable, is the set of all possible values that the random variable can take on. And it could be discrete or continuous, so discrete if it's countable or finite, and continuous if it's uncountable. And that determines the type of random variable. Again, for now, we're going to be talking about discrete ones. So for any random variable, the cumulative distribution function, or CDF for short, is capital F of x, and that's the probability that the variable takes on a value less than or equal to little x, and it's defined for all values of x in the real line. So it has a value for every value of x in the entire real line, regardless of what type of variable it is. The CDF is always going to be non-decreasing, you can't lose probability, and it's going to be bounded between 0 and 1. For a discrete random variable, we also have a probability function, or sometimes called a probability mass function, and it's looking at the probability that x is equal to little x. And it's defined for all values of x within the range of the random variable. And we call that little p of little x. Sometimes people call it little f of little x as well, but in the course notes we use little p. So the probability function is going to have lots of properties as well. It'll be between 0 and 1, and if you sum them all up, it'll give you 1. Then we have the mean of a distribution. For a discrete random variable, we call the mean mu, or e of x, and it's just the sum over all possible values of x times p of x. And essentially, it's like the average value of the random variable. It's a weighted average where the weights are the probabilities of taking each value. And then lastly, we have the variance. So the variance of a random variable is called sigma squared, or var of x, and it's just the average squared distance from the mean. So it's officially the expected value of x minus mu quantity squared. But if we expand that square inside the brackets, we can also write that as e of x squared minus e of x squared. So that's commonly used to calculate the variance. Much easier to calculate in that second formula. And what this represents is how spread out the data is, or the distribution is, around its mean. A larger variance is going to be more spread out. And variance is always non-negative because it's a weighted average of squares. Next, I want to talk a little bit about Bernoulli Trials, which is a process that leads us to lots of different useful discrete random variables. So if you remember from Stat 230, Bernoulli Trials are a series of trials with 3 properties. The first one is that the trials, on each one, we can define it as a success or a failure. Secondly, the trials have to be independent. And thirdly, that probability of success must remain constant over all of those trials. So see if you can think of some examples of Bernoulli trials. Pause now and see if you can think of a few. All right, so now that we have some Bernoulli trials in mind, we have 4 different distributions that we can come from it. First is the Bernoulli distribution, or the indicator random variable, and we say that x is a Bernoulli random variable with parameter p if it equals 1 if a success occurs, and 0 otherwise. In other words, x takes on the values 1 with probability p and 0 with probability 1 minus p. It's a pretty simple random variable, simple as you can get other than a constant. And again, that probability p is the only parameter that we need. So we could show that the expected value of x is p and that the variance is p times 1 minus p. See if you can take a second and prove that now. Remember, using the definition of expectation, which is the sum over all possible values of the variable's value times the probability that equals that value. You'll get these results fairly easily. Next, we have the binomial random variable. So this is just where we take the number of successes on n Bernoulli trials. So it now depends on two parameters, n and p. And we can show that the probability function here is n choose x, p to the x times 1 minus p to the n minus x. And that's defined for all values of x between 0 and n. Logically, we can think about this. If we want the number of successes to be x, then we need n minus p of them to be failures. So that gives us the p to the x and the 1 minus p to the n minus x. But then those successes and failures can be arranged in n choose x ways. That's why we have the n choose x out in front. So we can find the mean and variance of the binomial random variable, our np and np times 1 minus p respectively. And we can get that in a few different ways, but note, if n is equal to 1, then the binomial just becomes a Bernoulli, right? N trials being one trial, we just have a Bernoulli. And also, if we have a collection of independent Bernoulli random variables and we add them up, then we get a binomial. Pretty neat. All right, third distribution we have is the geometric. So we'll let x be a geometric random variable if it's the number of trials required to obtain one success. And in this course, and most places, we define it to include that success. So the probability of x, the random variable, equaling little x, the value, we would need to have x minus 1 fails and then one success, because x includes the trial on which that success is obtained. So obviously the range is going to start at 1, because the best you can possibly do is get a success on the first try, and then that would be x equals 1. So the range again is 1, 2, ... There's no maximum. We could continue getting any arbitrarily large number of fails before that first success, but the probability function is again 1 minus p to the x minus 1 times p. We can also find the mean and variance. The mean is 1 over p, and the variance is 1 minus p over p squared. And again, see if you can try to prove these results. These are a little bit neat and a little bit tricky. There's some fun ways to do it. I might actually ask you to do some of those proofs on the first assignment, so stay tuned for that. And lastly, for Bernoulli trials, we have the negative binomial random variable. So here again, we're going to let x be the number of trials required to get not one success, but r successes. There we go. And so similarly, we can find the probability function, x minus 1 choose r minus 1, p to the r times 1 minus p to the x minus r. Again, because we're counting the trials on which we obtain those r successes, the range of the random variable starts at r. So it could be r plus 1, r plus 2, etc., but there's no maximum. And we get this probability function kind of similarly to how we got for the binomial, but a little bit different. So again, if we're going to have it take exactly little x trials to get those r successes, we know that amongst those trials, we need r successes and x minus r fails. So that's where the p to the r and the 1 minus p to the x minus r comes. But we know that the very last trial has to be a success. Otherwise, we would have stopped counting earlier. So in terms of the ways that they can be arranged, there's only x minus 1 choose r minus 1 ways that those successes and fails can be arranged, because the very last trial has to be a success. Again, if you're a little rusty on that, maybe review your Stat 230 notes. We can also find the mean and variance of the negative binomial. The mean is r over p, and the variance is r times 1 minus p over p squared. And we can get that in a lot of different ways, but again, we can use the relationship between the geometric and the negative binomial, which is going to have a similar relationship to the binomial and the Bernoulli have to each other. We could sum up a bunch of geometrics, and that would give us a negative binomial, and so we can get these nice results here. So lastly, I want to talk about one last random variable that does not come from Bernoulli trials. And this is the Poisson random variable. So we'll say that x is a Poisson random variable with parameter mu as the number of events that occur by time t in a Poisson process with rate lambda. And mu is just equal to the product of lambda times t. In this case, we end up with the probability function being e to the negative mu, mu to the x over x factorial, and the range is actually 0, 1, ... no maximum. So we will talk a lot more about the Poisson process when we get to chapter 5 and look at a lot more details of it. But if you remember from Stat 230, a Poisson process is just events occurring randomly throughout time or space that are independent of each other, that have a constant rate of occurring, which is that rate lambda, and that are stationary, so that rate doesn't change over time. And also the events can only occur one at a time. So we can't have two events happen simultaneously. And again, we can derive the probability function here. We can show then that the expected value and the variance are actually both equal to mu, and see if you can prove that. All right, lastly, I want to do an example using all of these different distributions. Imagine that trade requests come into a trading desk according to the conditions of a Poisson process with a rate of 4 trades per hour. So pretty slow. We're going to say that an hour is quiet if no trades occur during that hour. So if there's no trades in that hour-long period. And I want to find the probability of lots of different things. First of all, the probability of a quiet hour. Second, the probability of 2 quiet hours in an 8-hour day. Third, the probability of needing to wait 6 hours to get 1 quiet hour, and that means 6 hours total. And finally, waiting 7 hours to get 2 quiet hours. So before I show you the solution, get a pencil, get a paper, give this a try. This is a review of Stat 230. Again, it might be a little rusty for you, but you should be able to identify which distribution to use for each of these 4 parts. And spoiler alert, they're all different distributions. So give that a try and then come back. All right, let's give it a try. So for the first part, we're going to let x equal the number of trades that occur in a 1-hour period. And obviously, because of the way we've defined this process, x is going to have a Poisson distribution. It's literally the number of events in a 1-hour period in a Poisson process with rate 4. So that's a Poisson distribution with parameter equal to 4 times 1, which is 4. And then we want to think about what we want. So for part A, the probability of a quiet hour is the probability that x is equal to 0. So we can plug in our probability function for a Poisson. We get e to the negative 4, which is 0.0183. And this structure of, define your random variable, find its distribution, and then say what you want in terms of that random variable is going to be a really helpful structure for all sorts of probability-related questions. So for part B then, let's do the same. We're going to let y equal the number of quiet hours in an 8-hour day. So we can think about these 8 hours as 8 individual trials, right? Non-overlapping hours back to back. And because of the properties of the Poisson process, those 8 hours are independent. They have the same probability of having a quiet or of being quiet. And they also are either quiet or not. So we have all the conditions here for y to be a binomial random variable. We have 8 trials, and the probability of success, being quiet, is what we calculated in part A, that 0.0183. And then what we want for this question is the probability that y is equal to 2, because we want 2 quiet hours out of 8. So we'll plug in this probability function, and then we get 0.0084. For part C, we want to let z equal the number of hours it takes to get that 1 quiet hour, that first quiet hour. So again, here we have all of the conditions of Bernoulli trials. We have independent hours that have the same probability of success. And we're talking about waiting until we get the first success. So z is going to be actually a geometric random variable with probability of success 0.0183. And now what we want is for z to equal 6, because we were looking for that. So again, we plug into the probability function and we end up with 0.0167. Finally, for D, let's let W equal the number of hours required to get 2 quiet hours. And now similarly, we can see that W is going to be negative binomial with parameters 2 and 0.0183. And we want the probability W is 7. So again, we can plug into our probability function and end up with the result of 0.0018. So hopefully this structure of defining your random variable, stating its distribution, and then figuring out what you want in terms of that random variable that you've defined, and then plugging in the probability function is going to be a helpful structure for solving this type of problem. That's everything for this video and for this week. I will see you at the tutorial 1 on next Wednesday at 9:30, and we'll have a chance to play around with some of these ideas from these last 2 videos. Have a great week and see you then.